everybody, this is Gerard doing the binary search tree assignment. Um, I'm going to post this in the binary search tree discussion just so you guys can see what I have, and then I think I'm also going to post the source code just so people can see what's going on and have some references out there, because the online references are good and all, but I think just collectively as a group, students helping students is good. So the implementation, got to make a data tree structure, um, binary. Then you have to make sure you have insert, delete, maximum, to find the maximum value in the binary tree search, binary search tree, sorry. And then you have to traverse it, and you can do this with an in-order, pre-order, or post-order traversal. I did in order because I used my maximum as a way to find my in order in a sense. So what I mean by that is my in order uses my maximum to constantly sort it out in order. So it's going, is this the maximum? Is this the most extreme for left or right? And it says yes or no. And if that's the case, then it tacks it on into the right node. So that's how I used my maximum. I didn't use it in a traditional display to user sense. And you'll see that inside the code. So let me just get into some of the code. Minimize. I'm going to start all the way from the top, just so you see. A little bit more comment organization here, just because it's a hefty piece of code right here. It's all on one main. I did. Pardon me. I did not want to use multiple headers and all that stuff, and make classes all on their own. You could split up the class to its own. I did not use structs this time, just to demonstrate that you can do it with structures or classes. And I used the classes one. The big key note versus structures and classes, which if you've taken the object-oriented program section yet, you would know, is I had to put public here. Structures are normally public, classes are normally private unless you say it's public. So if you're having issues with that, that could be why. Just a little snippet. I was having a lot of issues. I was like, I can't find that. And I was like, why? It's up there. That's because I normally use structures for stuff like this. That's just data. Um, and not classes. I use classes for things that need to get changed quite often. But so we have our class node. So just like the linked list, the only difference is that binary structures is a linked list that splits itself over and over and over again, right? And so let's continue through. So if you see here, I have the class nodes and the recursive functions kind of tied together, because it goes class node, and then all the recursive function is just a pointer to the function inside of, almost not inside of the class, but we're referring to the class, and then you just pass it like normal function. I have normal functions as well up here that are declared, so that way everything will make sense. So let's just go through the first one. The first one I have is a search, and all it's doing is it's taking in the data that the person wants to search for. And it just goes through and it takes a temp node equal to the root, which is equal to the, when I say the root, if you picture a small binary tree, literally just the initial and then the two children. So the root is technically the parent, right? So just keep that in mind when you see root from my coding. So while the temporary node is equal to null, which is currently the root, while the root is equal to null, if the data equals the temporary node, change that data, and then return temporary node. So basically, if data pass equals the node data, return data in node. If the data is less than, look down to the left. If you could put in here, if data is greater than, look to the right child for what you're looking for. I just did else because there's nothing else. We're doing binary, so it's you're either going left or right. Nothing else. If apologize. If you were doing this with something that was not binary, you would have to actually go through and do this. So just keep that in mind. Let me zoom in for you guys while I can so you can see stuff. Um, if no key is found, so if no data is put in here to be put into the temporary node and then looked back and forth, right, and to the next nodes, then no value in tree, return null. So just return null, be like, hey, the number you're looking for inside of this tree doesn't exist, right? And that's basically all search is. Class node in predecessor. So all this is used inside of, what is it? Delete. Yeah, delete. And so basically, this is just taking a node from the class that's passed in, right? And if it's null, it's just relinking it to another node, the previous node, so that way it can be deleted. And you'll see this more in form. So the predecessor is the one before this parent, and the successor is the one after this parent. Basically the same thing. Um, One thing to note is that predecessor is right and successor is left, but they basically do the same thing, and they're going to return just the node that you're looking for above or below so that you can link it in delete. And here's where that happens. So here's the delete recursive function. Sorry, I have a bit of a runny nose. Again, another temp node. You just need that for just holding values and stuff like that and playing within your little function. So if the root node and then data, right? Key is data. So root node and then data. So if the root node equals null, so if the parent node equals null, just return null and be like, oh, there's nothing there. There's no parent next. There's nothing here. If the root node is equal to null, so if the left child of the root node is equal to null, and the root child to the right is equal to null, left and right child is null, right? Bam. Then do this, okay? And so this is just so you can delete the leaf nodes. So this is the nodes at the very end that don't have a child in general. It's just like, I don't have a right child or a left child. They technically do, they're just not equal to anything, which is why it's called the leaf node, right? It's just chilling out there. So technically, you could have a root node with no children, and that is a root leaf node. Um, if the node equals the root, if the pass data is equal to the leaf node data, change the root to equal nothing, right? Because we're getting rid of it. Free up the memory space of this leaf node, which is the root node, right? The parent node, and then return nothing. So it's just deleting and freeing up memory of the leaf node. This is if it is not a leaf node. If the value of the data is less or greater than the value in a node, right? That's all this is doing here. If the data passed in is less than the node data, go to the next left node, right? If the data passed in is greater than the node data, go to the next right node. Else, and here is where you're taking the predecessor and the successor and relinking them up after you delete. So you're going to delete the node and then relink it. And that's all it's doing. Temp node equals previous node, temp node equals new root with the data in it, and then delete the old node and relink it, right? And then same thing for the next node, which is right and left. So previous would be the left node, and next would be the right node. Then just return the value of the root, the new parent, right? Return it. Bam, there it is. That's the new value. Then we have the declared functions actually down here. So we declared them up top, and here are the declared functions themselves. So this is to insert. This could be a recursive function. So like up here, this could be class node point insert, and have actually quite a bit less code in it. I just wanted to show multiple ways of doing it. Um, so this is just taking in the data, right? And then we have class node, so temp node, scan node. So the temp node is going to be equal to the root, the parent, right? And then scan node, which is equal to null. So it's just the nodes that it's scanning through. Bloop, 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 bloop. Next, 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 next. And it gets loaded into scan node. So it's just basically a holder for me. And then a pointer to create node. So then we're pointing to a new node that gets created, right? So if there are no nodes, right? We have no tree yet, no roots, nothing, right? We're just starting. This is what's going to happen. Create the first node. So you're going to create the first node, allocate memory to it. You're going to insert pass data to the nodes, which is through key, boop, right there. And then you're going to create the left and right children of this node, and then the root is going to be the new created node, right? And then bam, there we go, return, done. Return to main, or return back to finish this, sorry, this function. So what about if there is already a node? So if there's already a node, while temp node is not equal to null, right, is something there, we're going to scan through the nodes, and then temp node is going to be equal to the scanned nodes. So scan nodes equal to temp nodes. Identify and assign data to the correct child. So what's happening here is during the insertion, my tree kind of automatically assigns left as high. Wait, hold on. If key is less than itemp node, yeah. So sorry, left is low, right is high. So the left nodes are always going to get the lower number. The right node's always going to get the higher number. Okay. And so that's all that's saying is if the value is less than the temporary node data, then make the child to the left, right? So if I have a 10 and I put in a 5 and a 6, the 5 is going to go to the left, the 6 is going to go to, it would actually also go to the left, but because of the root node. But if you were to put whatever the root node is, so let's see if our root node up here, our first node was 10, and then we put in a 5 and a 20, 5 would go to the left, 20 would go to the right. Okay, and that's all that this is doing. It's just passing in and assigning left to right for the children. Create node, it's identical to the first node, and this is just the creation again of the child node, right? Reallocating memory, inserting the data into node, and then creating the left or node. This is identifying what it is, and then this is creating it, right? So next is connect the links to right and left nodes, and this is all this is doing is, again, same logic as up here. If greater than, connect to the or if less than, connect to the left node. Else, connect to the right node, right? Because it's only binary, only two. If this was more, we'd have to go through an entire statement here of if, else, else if kind of stuff, right? The next one is print binary tree in order. This is technically just an in order one. The only reason I say print is because I added the print feature in here because it's just easier to do it in here. But if currently passed, right, the node currently passed, root node, the parent node, if it's currently passed from the class, right, if it just exists, which is what that says, insert the value to right and print for each, right? And so it's going through and it's putting into the left node the data, printing it, right node, and then same thing. So it's just printing out all the data for right and left node. What is next? Find the max and return the max value of either node. So this is my max class, and it gets used up in, where does it get used? Shoot. It does get used, I swear. I swear it. Oh, yeah. Okay. So it gets used. Maybe I'm losing my mind. I know I have it. Max. Sorry, this is where it's getting chaotic, right? Oh, here it is. Bam. Very small piece. Boop. So if the max of the left node is greater than the right node, right? And so this is just finding the max. So the end, the most extreme of the left, which would be the lowest, and the max, the most extreme of the right, which would be the highest. And then it has the condition. So if the lowest of the low is higher than the high, is greater than the highest of the high, then do this. Otherwise, do this, right? And so that's what that's doing. And that's how I found my max. But we'll go through it. Let me find it again real quick. Bam, max. So find the max, return the value of either node. Variables for max. So I just did a left, right, or left max and a right max. If the pass data is equal to null, return null, right? So if the root passed in, if its value is nothing, return nothing. Simple, right? Keep it as it is. If the left, we want the left max to equal the maximum of the root node, so the node that was passed in of the left child. So we're taking the left and we're turning the left max into what the left child's value is, right? We're taking the right max and we're maxing it recursively, or not recursively, sorry, not recursively. So we're taking the right max and we're equaling it to the right of the node that was passed in, right? And so that way it goes through each one of the nodes and it keeps getting higher, 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 higher till it finds max and it's done, right? And then we're returning the left, which is greater than the right, just making sure that it is, and then we're just returning left plus 1 or right plus 1 as a value back, so that it can be used in the algorithm up top. And then we have main, and so main is very, very simple. You could load all these things into functions, but I just had it here so I can also show people what's going on. So we have our instance pointer of class node, so I just name it what it is, very literal with my variables and instances and stuff like that. And so we have insert, and we're just inserting 10, 5, 20, 8, 30, and 100. So just as I was saying, our root is 10. That's a good base, right? So 5, gonna go to the left of 10, right? If 10's a parent, right? It's in the middle here. 5 is gonna go over here to the right. Or, sorry, to the left. It's gonna go over here to the left. And then we have 10 again, right? 10 and 5. And then we put in 20. 20 is gonna go over here to the right. Bam. And then we have insert 8. So 8 is low, but it can't be in the right or left, so it's going to go down to the 5, and it's going to be to the right of 5 because it's higher than 5, but it's less than 10. So it's going to continue down this path. So technically, if we had 10, 5, right, and then we did 6, 7, 8, 9, 6, 7, 8, 9 would continue down the right side until we got back to 10, and then it would just place it to whichever side. There's no real side that it would go to. 100 would be to the right of 30. 30 would be to the right of 20, so on and so forth. And I wish I should have a better viewport of this for you guys, but you'll see it once we get there. So that's step 1, just inserting basic roots, and then bam. Step 2, traverse. I did the in order method, and then I did the print tree, right? So in order, it's going to print tree, and then just formatting. Step 3 is going to be search. It's going to be the instant pointer. We're going to search for the number 20. We're going to search for 100, and then it's going to tell us if it found it, and then it's going to tell us if it didn't find it, right? Same thing for 100. Step 4, we're going to delete 20 and 100, and then we're going to search for them again. Is it there? And it's going to tell us if we did or did not find it. Same for 100 again after we delete them. Step 5, we're going to just remove the leftover roots that are in there, the leftover parents, and then we're going to print it. And nothing should come up, so we shouldn't even see this. Should be absolutely nothing, which will be great. Then we're going to have the step 6, which is a little bit of the extra credit. I did an int, I did random using the C library stuff. It's going to give us random numbers. And then I did I for null, and it's just my counter variable. And then I just did a for loop, and I did it, what was it, 100,000 times? Boop. So 100,000 times twice, because technically it's doing two versions of it. It's loading high numbers and low numbers from 1 to 100,000. And then just some fun number equations in there to give us even more of a random number, because the .ran gives numbers based off of time and all that stuff. But and so it's going to give us 200,000 numbers inside of this tree. And it's fun to watch on how that's noticeably and visually long. And then we're going to print it, right? Which is the actual length of it going through that. And then use I just use get char to pause program, so nothing crazy. So let's actually just run this. Um, yeah, let's just run it. Main. So I'm going to go to Analyze. We're also going to go to Performance Profiler. I'm going to just do CPU usage. It'll give us the time frame for it. It's going to have a stop numerous times. Not for the profiler. See, this is all the random numbers. Isn't that crazy? Boom, done. And the reason you're like, well, how come it's not just repeating or doing garbage? And that's because A, it's not repeating because it stops, right? You got something, nothing, something, nothing. And then if you go all the way to the top, you can see it's sorting, 228, 2289, 2291. Again, it's showing you that there's random numbers in there. And then it even went into negative numbers because I did some funky math and wanted some really low numbers to show that that was a thing. And you can even see somewhere here, it flips at some point. Bam. Oh, here it is. See low numbers. Boom. Low numbers. Yeah, real fun stuff. I think I can spread this out just even more. See how crazy this is, all the numbers that it's given me. But either way, let's go over what it's doing real quick. So, diagnostic, yay. So we have here the the main, which used. Oh my goodness, there we go. Where is it? Where is it? There it is. Okay. So main used 29 milliseconds. That was across the board. Insert. This is the insert with by itself. The the big one that we used over and over and over and over and over again. So insert ran over the course of the program a total of 24 milliseconds. So 29 milliseconds is 100%, right? And out of 100% of that, out of that slice of pie of the entire thing, 24 of that was insert being used. So, I mean, that's pretty hefty. And so if we just look at what we got here, um, it'll just go through all these things. So let's see here. Here's where it spiked, right? Here's where insert really took a hefty toll on it. So then main's doing its job. It's using 98% of the CPU, right? 98 milliseconds, 98%, and then 63 seconds for the or milliseconds for the insert of all of the large data that we put in, right? And just as it goes on, it's crazy. Seconds, and then it just starts to die off. It levels off, right? It's just little things put in there. But this spike right here is where it gets crazy, and and you can actually just see all of the usage right here. It's insane. So I mean that's a hefty amount of usage. But if we go back here, we just look at what we got. So the insert, it put in, and you can see I inserted here at different orders. But the in order, right here in step 2, organized it. So the fact that those numbers are there means step 1 worked. The fact that they're not random, step 2 worked. Step 3, 20 is found and 100 is found. They're in the list, and it finds them. And then we remove them through delete, and then it looks again for each using the instance of search, right? And it's not found, not found, right? Cool. Bam. And then here should print nothing. Bam, line of nothing, because we deleted the rest of what was in there for the tree, and then we printed something, but there's still a line space right after this, but there's nothing to actually print. So there's no roots, there's no parent, there's no tree, just a skip line. So we skip it. Okay, skip to the end. And then we hit step 6, which is the random 200,000 insert of numbers into this tree, and then ordered it. And here you go. This is it. Bam. Just number after number after number after number after number. More numbers. Oh, we passed it. Bam. And then it actually kills out right here, ending with 100,032,702. So this visually took a long time. This is doing stuff that doesn't even need to be rendered, right? Can you imagine, like, if this were in a game or something that needed more processing than just a random number assignment? But in the end, the it was just, I don't know. There's a lot of stuff going on in here. Pointers weren't too bad. You get used to it after the linked list, and then just the time analysis is just interesting once you really overload it with numbers. If we were to just do this with, just to give you a really quick, I'll change it back. We're gonna just do this with 1,000, right? We'll just change all this to 1,000. We'll pretend that that's not a thing. Do the local debugger, right? Wow, it's gonna want me to do all these things. Bam, 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 bam. We'll get through. I had breakpoints because I didn't know if I needed them or not during the bam. And so this is the significantly less time. Like, it literally, I could just click to it, as the other one rendered, not rendered, but processed, hundreds of thousands of numbers. This one was just 1,000 numbers, which is still a lot there, but nothing in comparison to what this was. We'll remove the breakpoints again, and I'll show it to you just one last time in full blown. Go to, I guess I could have just hit remove all, right? Delete breakpoint. Oh man. So I can have nice things. So, but if we just go back here, I'll just add two more, right? 1, 2, 1, 2, 1, 2. I just watch this. It's just mind blowing to me. Bam. It's visually longer. It's just noticeably longer, and you're like, anytime now. Bam, done. Versus the 1,000. So, the input, I would say this is probably n. This is probably unfortunately n squared, for sure, because it's based on amount of stuff per time, and not just the same amount of time regardless of what's in it. So that said, though, that's the end of this project. I'm going to do a quick save so I don't lose that. On the solution, save. Oh my goodness. Oh, I don't want the report, that's why. Boop. Yes, close out. No. And no. Save. We'll minimize that, bring this up. But if you have any questions, just let me know. I will post my source code in there, just so people have it, though. And have a good one.